Welcome to Next Gen Manufacturing. If you've ever been on a modern airplane, you've literally trusted your life to some of the most advanced materials on the planet. But have you ever stopped to wonder, how do we know for sure that those super light, super strong parts are perfect on the inside? Well, today we're diving into the incredible tech that lets us do just that by seeing with sound. So let's just jump right in with a puzzle. Picture this. You've got a critical component, say an airplane wing made from these space-age composites. You have to be 100% certain it's flawless, deep inside. The catch, you can't cut it open to look. So what do? How do you find a problem you can't see? Well, the answer has a name: non-destructive testing, or NDT for short. It's basically the science of looking for invisible threats. Tiny cracks, bubbles, weaknesses, without leaving so much as a scratch. You can think of it as a high-tech physical exam for the most critical parts in the world. And this is so important because these new materials are amazing, right? They're like this high-tech plywood with layers bonded together to get this unbelievable strength without the weight. But, and it's a big but, if even one of those layers starts to peel apart, or if tiny air bubbles get trapped inside during manufacturing, you've got a hidden weakness, a weakness that could lead to a catastrophic failure. The stakes here are as high as it get. This brings us to a really brilliant solution: ultrasonic inspection. The logic is simple, right? If you can't see a flaw with light, maybe you can hear it. It's kind of like giving the machine a superpower, the ability to listen for problems buried deep inside a solid material. Okay, but here's a fun little quirk of physics you have to solve first. These powerful ultrasonic waves, well, they just can't travel through the air. They need a medium. So to get the sound from the machine into the part you're inspecting, you need some kind of bridge. And in this case, that bridge is a carefully aimed jet of water. It creates this perfect connection for the sound to travel from the machine into the part and then back out again. At its heart, the idea is just wonderfully elegant. A little device called a transducer sends out this pulse of high-frequency sound. We're talking way beyond what any person or even a dog could hear. That little sound wave zips through the part, and all the system has to do is listen to what comes back. Any change, any echo, any little bit of signal that gets lost along the way. It all tells a story about what's going on inside. So, when an inspector actually goes to listen for these hidden flaws, they've got two main techniques in their toolkit, and each one is good for finding different kinds of trouble. On one hand, you've got the transmission method. The easiest way to think about this is like shining a flashlight through a pane of glass. If everything's clear, the light goes right through. But if there's a crack, it blocks some of the light. Same thing here, but with sound. A flaw blocks or weakens the signal. It's great for things like honeycomb structures inside a wing. Then you have the reflection method. This one's more like sonar in a submarine. Bing! One device sends out a pulse and then just listens. If that sound wave hits a defect, an echo bounces back. Bing! And that echo tells you not just that there's a flaw, but exactly where it is. Now, those basic principles have been around for a while. But in the world of next-gen manufacturing, you need to inspect enormous, incredibly complex parts, and you need to do it fast. That's where things get really clever. So, problem number one is just pure time. Can you imagine trying to scan an entire airplane wing with one tiny sensor? It would take forever. The solution? A patented multi-nozzle system. So instead of just one little beam of sound, it sends out a whole array of them, scanning a much wider area all at once. It's a total game changer. And get this, with this system, you can scan a 1 meter by 1 meter square down to 1 millimeter precision in just 30 minutes. That is an absolutely massive leap forward in speed and efficiency. It's exactly the kind of innovation that makes next-gen manufacturing possible. Okay, so speed is one thing, that's great, but what about complexity? An airplane's body isn't a big flat table. It's got all these complex curves and shapes. You can't just tell a robot to go back and forth in straight lines. So, how does the machine adapt on the fly? The answer is so cool. It's a technology called profile following. And what it does is, instead of needing a pre-programmed 3D map of the part, the system uses its own ultrasonic signals to feel its way across the surface in real time. It's like it's navigating by touch, using sound. It all happens in this beautiful 3-step dance. Okay, step 1. A central sensor is constantly pinging the surface, just to make sure it's keeping the exact perfect distance away from the part. Step 2. 4 other sensors around the outside act like a balancing team. By instantly comparing how long their pings take to come back, the system knows if it's tilted even a tiny bit, and it adjusts to stay perfectly perpendicular to the surface. And finally, step 3, tiny motors are making constant, real-time adjustments, changing the position and the angle so the nozzle head just glides perfectly over any curve the part throws at it.
So the scan is done. The robot has done its elegant dance. Now what? Well, now you've got this mountain of invisible acoustic data, and you have to turn it into something a person can actually understand and make a decision on. You have to create the map to safety.
And what are we hunting for on this map? We're looking for the silent killers in these materials. Things like delamination, where layers start to separate. Porosity, which is just a fancy word for clusters of tiny air bubbles that create a weak spot. We're looking for bad adhesive bonds, dents in the internal structures, and even, believe it or not, foreign bodies, like a tool or a bit of debris that got trapped inside during manufacturing. And all of that data gets compiled into one single powerful image. It's called a C-scan. The best way to think of it is as an X-ray, but made with sound instead of radiation. It's this top-down, color-coded map of the part's guts. Healthy areas might be a solid green, for example, but a flaw, a defect, will show up as a bright red or yellow spot. It's an unmistakable anomaly, but it still takes a trained human eye to know what it means. Because that's the thing, for all of this incredible, mind-blowing automation, this is the moment the machine hands the baton over to a human. This high-tech map is just a pretty, colorful picture if you don't have a highly trained, certified expert who knows exactly how to read it. And we're not talking about just any technician. These inspectors go through rigorous certification. A Level 1 is certified to actually perform the scans following a strict procedure. A Level 2 can go deeper. They can set up the equipment, calibrate it, and even help develop the inspection plan. And then you have Level 3. These are the true masters. They can direct entire NDT operations and even establish the rules for what's acceptable or not on brand new materials. And in the end, after all that tech and all that expertise, it all comes down to a simple final decision. Is this part good to go or not? The official report makes the final call. It defines acceptance or refusal. There's no gray area. It either passes or it's rejected, period. And that right there, that's really the heart of the story. The incredible safety and quality we have in modern manufacturing isn't just about the amazing robots, and it isn't just about the brilliant experts. It's about the powerful partnership between the two, the flawless precision of the machine combined with the irreplaceable judgment and experience of the human. Which, of course, leaves us with one last thing to think about. We are constantly inventing new materials that are smarter, lighter, stronger, and way more complex than ever before. So the real question isn't just about the amazing technology we have today, it's about what we'll need tomorrow. As we keep building the future, how will our methods for seeing the invisible have to evolve right alongside it?